Now continuing on the same phase, the voltage across the resistor is given by the equation VR2 is equal to R2 by summation R multiplied by E. Okay. So what we understand from this? So we have an applied voltage of E, and this voltage is shared. This voltage, just a minute, I'll rub it off all this so that we will have a clear picture. Okay. Now what we understand from this, we have an applied voltage of E, and there is a series resistors R1, R2, R3. Okay. And the applied voltage is shared across these resistors. The voltage is divided across all the three resistors, and therefore this particular is called as a voltage divider rule. So how will you divide the voltage? There is an input voltage of E, and there are three resistors. And if you want to calculate the voltage across any particular resistor, then my VR1 is given by that particular resistance R1 divided by summation of resistance sigma R multiplied by the input voltage. So this is called as an voltage divider rule, and we find a lot of applications where we will use this voltage divider. Okay. Now, while I'm discussing, I would say that this is the series circuit. So what are the characteristic features of a series circuit? So the features of a series circuit, I can say that in the series circuit, current is the same. A single current is flowing in the entire circuit. How will you define series? If you have two resistors like this, the end terminal of the first resistor is connected to the starting terminal. So when you do a connection like this, it is called as a series circuit. And the voltage across any resistor is given by the Ohm's law, the current into resistance, and this VR1, the voltage across a resistor, any particular resistor is given by that particular resistance value by summation. The summation I can call it as R equivalent. So where R equivalent is given by R1 plus R2 up to RN, and this I can write it as I is equal to summation I is equal to 1 to N Ri. Okay, so if you have N resistors, the equivalent resistance is given by the addition of all resistance. Okay, so I have taken some simple problems where we could understand what is the potential difference and how to calculate the total resistance. A very simple problem. Okay, so this is what a problem. It is required to calculate the potential across this point A and B, and that is a combination of three battery, 1 volt, 3 volt, and 5 volt. Okay, so when you are moving from A to B, you have to observe the direction in which we are moving when you are across the battery. Okay, so for battery 1 volt, you are moving from minus to plus, so it is a potential rise. For battery of 3 volt, you are moving from plus to minus, so it is a potential drop. And for battery of 5 volt, you are moving from minus to plus, so it is a potential rise. So potential rise to be given positive, potential drop to be given negative. So this is plus 1, minus 3, plus 5. So when I combine positive and negative terms, 6 minus 3, and the net voltage VAB is equal to 3. So this is how we assign polarity for the voltages, and we calculate the the net voltage across any 2 points. So this is one kind of a problem. And this is the NPTEL problem, National Programming on Technology Enhanced Lab. Okay. So this is another problem where you have a series connection of resistances 6, 10 and 8. So what is the equivalent resistance? Summation of all these three. So 6 plus 10, 16, 16 plus 8, 24. Right. And the next one, it is required to calculate what is the voltage across this element. So it is not necessary to calculate the current and then multiply the current with this 4 ohm. I can directly apply the potential divider. So what is my potential division? The voltage across any element is equal to that particular resistor, that particular resistance divided by the total resistance summation or multiply by the input voltage. So summation of input voltage. Okay. So my input voltage is 10. So 10 I have written. I want the voltage across 4 ohm. 4 I have written here. What is the total resistance? 10 ohm. So 4 by 10 multiply by 10. So 4 volt is the voltage available across this 4 ohm resistor. So this is how we apply the potential divider or the voltage divider rule to calculate the voltage across any particular resistor. Okay. So now we will move on to the another terminologies, the glossary. What is meant by power? So power is almost the energy transferred or converted per unit or rate of doing work. And the SI unit of power is watts. And this is 1 joules per second. Joule per second or E by T. Or this also can be represented as rate of doing work with respect to time. So W is the work and delta T is the elapsed time, right? And another important terminology normally we use in electrical engineering is the energy. Energy is defined as the product of power and time. And the power can be an instantaneous power or an average power, right? So instantaneous power is at any particular time, what is the power any particular load is consuming. And the average power is the total energy divided by the total time. And the unit of energy is, actually energy is measured in watt hour, but watt hour is a very small unit. So you measure the energy in kilowatt hour, and 1 unit is called as 1 kilowatt hour. So 1 kilowatt hour of energy is called as 1 unit of energy. Okay. Okay, so now we will move on to the next topic. Next part of discussion is on the parallel circuits. Okay, so this shows the parallel circuit. Now, how will you identify the parallel circuit? So I have 2 resistors like this. I have 2 resistors like this. The starting end of 2 resistors are combined together, and the ending end of 2 resistors are combined together, connected to a common voltage source. So when you do like this, this is called as the parallel circuit. Okay. See, for the parallel circuit, the voltage is common. Like in the series circuit, current is common. In the parallel circuit, voltage is common. So the current delivered by the battery is I, and current flow through this resistance R1 is I1, and through the resistance R2 is I2. Okay. So the current obeys the KCL, right? So at this point, at this junction, current entering is I and the current leaving is I1 and I2. Therefore, I can write my KCL as I is equal to I1 plus I2. Now, what is my I1? I1 is the voltage divided by the current. So for this R1, voltage is equal to V. So I1 is V by R1. And what is my I2? I2 is V by R2. And if I try to write the summation, I is equal to V by R1 plus V by R2. Take V outside, 1 by R1, 1 by R2 multiply by V. And this I can write it as V by R equivalent, where this 1 by R equivalent is given by 1 by R1 plus 1 by R2. Now, if I take the LCM and simplify, the R equivalent, I can write it as, if I take the LCM and simplify, R equivalent, I write it as R1, R2 divided by R1 plus R2. R1, R2 divided by R1 plus R2. Right. So the total current supplied by the battery is given by the equation. I of t is equal to V divided by V multiplied by 1 by R equivalent. So if I substitute R equivalent is R1, R2 by R1 plus R2, this is what my equation. So V is equal to IT multiplied by R1, R2 by R1 plus R2. Okay. Now going back to the diagram, what is my I1? I1 is V by R1. I1 is V by R1. Now V I can substitute from this equation. I of t R1, R2 divided by R1 plus R2, and writing this 1 by R1. So R1 and R1 get cancelled. I end up with the equation I of t is equal to R2 divided by R1 plus R2. And this is called as current division. Now how to keep memorizing this current division? Now let me say like this. The current through this resistor R1 is required. Then you have to write the ratio of resistance as the opposite value of resistance R2 divided by summation of resistances in the parallel circuit. So this is R1 plus R2 multiplied by the total current. Right? Similarly, if you want to take or if you want to calculate the current in this R2, you have to exclude that value of resistance, then opposite resistance, opposite path resistance, that I'll rub it off. So opposite value of resistance R1 divided by summation of resistance in the parallel circuit R1 plus R2 multiplied by the total current. So this is called as current division, and this is very, very important. So this is what I have given as a remembering tips. So for a parallel circuit, if you have two parallel paths comprising R1, R2, the current through R1 is given by opposite resistance by total resistance multiplied by the total current, and this is the current divider rule. And voltage division is applicable only when you are having a series circuit. The resistors are connected in series. Voltage across the resistor is that particular resistor multiplied by the particular resistor divided by the total resistance multiplied by the input voltage. So you keep these 2 points in mind. Okay. Now, my next point of discussion is on the sources and their classification. So the sources are classified as, in a major classification, sources are classified as the voltage source and the current source. The voltage source and the current source. Again, there is a classification of 2. The ideal voltage source, practical voltage source. And in the current source, ideal current source and the practical current source. Okay. So what is an ideal voltage source? So this is what the definition of an ideal voltage source. The ideal voltage source is a 2-terminal device where whose voltage at any instant of time is constant and is independent of current drawn from it. So whatever the current supplied by the battery or whatever the load connected to the battery, the voltage across the battery terminal is constant. Okay. So, but by virtue of practically an ideal voltage source could not be obtained. So there is another voltage source called as a practical voltage source. Okay. Now, sources having some amount of internal resistance are known as practical voltage source. Okay. Now, because of this internal resistance, the voltage drop takes place. Okay. So this represents the ideal voltage source. So you have a battery and this is my output voltage. The output voltage is equal to the battery voltage or the E, then it is called as a ideal voltage. There is no drop, there is no internal resistance. So my internal resistance Ra equal to 0. So this was the characteristics of an ideal voltage source. Okay. So if to the same circuit, if a load is connected, so current flows through this load is IL, V0 is the terminal voltage, and VL is the voltage across the load. Okay. Now what is my IL? IL equal to VL by RL. And since VL, V0 are at the same potential, I can write it as V0 by RL. And for an ideal source, V0 equal to E. So V0 equal to E, then IL is given by E by RL. Okay. So whatever the connected load or whatever the current taken by the load, the voltage E remains constant. Voltage E remains constant. Okay. So now coming to the practical voltage source, my practical voltage source will look like this. So there is going to be an internal resistance of Rs, and this will create an internal drop. Okay. So when there is no load is connected, the V0 is called by the name VOC. So for a practical voltage, this is what a condition. This is what a condition. The terminal voltage or the open circuit voltage will always be less than the battery voltage. Why it is less? There is an internal drop. So this VOC is given by the equation E minus IL into RS. And if you connect a load to this particular practical voltage source, so VL is the voltage across this load terminal, which is given by IL into RL. My IL is equal to the total resistance RL plus RS. And if I write this, the load voltage, it is given by E multiplied by RL plus RS, right? So because of an internal resistance, there is an internal drop and the output voltage is always less than the battery voltage. Okay. Now let me discuss about the characteristics of ideal voltage source. So this is the ideal voltage source and this is the practical voltage source representation. So when I say that an ideal voltage, my source resistance is equal to 0. And if I say a practical voltage source, there is a minimum amount of source resistance available. Now, how to draw the characteristics? When I try to draw the characteristics, VI characteristics for an ideal voltage source, it will be looking like this. So my irrespective of current or time, my voltage remains constant. But for a practical voltage source, so there is a drop because of a source resistance, and this dotted line is a constant voltage, and this line is representing the voltage output from the practical voltage source, and this distance is the drop. This distance is known as the drop occurred in my source resistance. Generally, these ideal voltage sources, example of ideal voltage source, sorry, practical voltage sources are normal batteries, alternators, etc. Okay. Now coming to the current source. Okay. So again, ideal current source, practical current source. So sometimes it is required, sometimes to generate a definite and constant value of current. Instead of an voltage, I require current to derive the voltage. For example, my cell phone charger, where even if I'm saying the charging, my voltage is increasing, but the process of charging takes place by the current delivered by the supply to my charger, right? So the representation of a current source, either I can use a circle, a two circle like this, or I can draw a circle with the arrow mark representing. This arrowhead represents the direction of a current, or this point is positive with respect to this point. Okay. Now, generally current sources do not occur naturally. So we don't have any particular device like battery. It is an example of a voltage source, but I don't have any example of a current source, but I can develop my current source, right? So the current sources are constructed using electronic circuits. In turn, they are powered from the voltage source. I will have some rectifier which is supplied from my main supply, AC supply. So there is some conversion process is happening in the current source. So in this ideal current source, this current supplied by the battery is IS, current delivered to the load is IL, and for an ideal current source, IL equal to IS, right? So example of a current source is the battery charger. So this is how the process is happening in the battery charger. So I am taking the supply from my AC. I'll connect my charger to the socket. So there is a AC supply available. Some conversion mechanism happens here, and I'm getting a current that will charge my mobile battery. So here the load is my mobile battery, and this is what my current charging. Okay. And if I move on to the practical current source, so like the current received to the load will be less than the source current. So for example, generally current is analogous to the water flow in the pipe. So if the pipe is not having any holes, whatever the current taken from the tap will reach my bucket, right? And if there is any leakage in the pipe, so there is going to be a leakage water, and that will be known as the internal resistance. So this internal resistance will be connected parallel to the current source, right? So for a voltage source, it will be connected series, but for a current source, it will be connected parallel. So this is my source, and this is my source resistance, and this is load. So there is always a current flow through this internal resistance, and a lesser part of a current is reached here. And if I try to draw this VI characteristic of a current source, so I here voltage or time here. So this is constant for a ideal source, and there is a dropping in current for a practical source.